Good afternoon. Today we are going to see one problem that is from footing. We have a column carries factorial axial load of 1400 kilonewton. Design an isolated rectangular footing for the column. Ultimate soil bearing capacity is 225 and the size of the column 300 by 500 millimeter. And materials are given M20 and Fe415. Now first we will write given data. We have given Pu 1400 kilonewton. This is safe bearing capacity. SBC means soil bearing capacity, and we have this as given as ultimate. If it is not given, if it is given only soil bearing capacity, you have to multiply it by 1.5 and then you will get it. Now, if you will go to some books, they are using this value as P. In that case, they are using SBC. So if you will use P, that is only axial load, then you have to go for P and then you have to use SBC, not ultimate SBC. We have to go soil bearing capacity in that case. So we have given Pu, then column size is given 300 mm by 500 mm and 20 Fe415. Now if column size is square, then you can go for square footing. Otherwise you cannot go for square footing. As calculations are easy, so we will go for square footing. You will not get marks for it. So now we have a rectangular column. So automatically we have this as a rectangular footing. Now step 1, we have area required. Now we know load. We know soil bearing capacity. So total load on footing. So total load on footing is load on column plus 10% load of column. Now this 10% load column we are taking as self weight of footing. So column load plus self weight of footing. So this becomes, so this is 1 plus this self weight becomes 0.1 and then we have load on column. So therefore we have this value 1.1 in which we have considered 10% as self weight of footing, and this not SBC, it should be ultimate SBC because we have this ultimate load. And from this we require area 6.84 meters square. So here I have mentioned that is assuming 10% column load as self weight of footing. Now we have second size of footing. So we have this column dimension BD and let PF, that is width of footing, and LF we have length of footing. D depth of column, B width of column, CXX and CYY, these are projection of footing beyond the column. So these are cantilever portions because we have this column and after this we have this footing, and therefore this is considered as, or this works as your cantilever portion. So now we will consider this horizontal as XX and this perpendicular to it as YY. You can consider reverse way also, whatever YY I have considered, you can go XX. So in books that is given differently. Now if we will see area of footing, so we have B, that is width of column plus 2 times CYY. So this is also CYY. So B plus 2 times CYY. And in the same way, perpendicular to it, we have D plus 2 times this is CXX. So 2 times CXX. Now to find the value of size of footing, we will assume projections, these are equal. So by considering projections equal, our bending moment in x and y direction are not differ a lot, and therefore it is always preferable. We will assume projection beyond column that are equal. And now from this, if we will substitute this value Cxx equal to Cyy as C, then unknown is only C, and we are in position to calculate C. And knowing value of C, we have that value as Cyy because C is Cyy and C is Cxx. And we are in position to find value of Bf, and we are in position to find value of Lf. Now here you have choice, you can assume values differently also, but in most of the books, they have given in this fashion. So by this equation, we are in position to find C and then size of footing. So we have substituted the value unknown is C, and we will get a quadratic equation. By solving this quadratic equation, we have value of C as 1.11. We will put it in BF because we have actually size of footing. So this I can write it as BF into DF, and that is equal to AF. And therefore BF is B plus 2C comes 2.52, and LF 2.72. We will round up it on higher side, and we will get dimension of footing, that is BF as 2.6 meter and DF as 2.8 meter. So provide this dimension, which will give us area provided of footing as 7.28 meters square, and we have required value 6.84. So this is greater than 6.84 square meter. So it's okay. So greater than 6.84 square meter. Therefore, okay. Then we have bending moment. We know as these projections are acts as cantilever beyond the face of the column. So for cantilever, we have formula that is Wx square by 2, where x is cantilever length. And then we are in position to find this bending moment. But for this bending moment, actually, we have to find the load, and that load, that is actual bearing pressure. So we have, that is column load. Now here do not take load on footing, you have to consider it value of Pu, and by this you have to find this actual bearing pressure on footing. So we have 1400 upon 7.28, which is area provided. It gives us actual bearing pressure as 192.31 kilonewton per meter, and this value always less than ultimate SBC. So 225, we have this value as ultimate soil bearing capacity. Now intensity of UDL along the length of footing, so we are going to get it as 192.31 into 2.6, because now if we will see, we have footing in this fashion on this area. Now we are interested to find UDL on this footing, and then we have this as 2.6 meters. So to find UDL, we have to multiply it by 2.6. That is width. And therefore we will get intensity of UDL along the length. For along the length, we have to multiply it by width, and along the width, we have to multiply it by length. So we have along the length, UDL will be 500 kilonewton per meter. And then bending moment at face of the column, we have W into Cxx square. W we have, that is actual bearing pressure, and Cxx, that is length beyond face of the column, that is cantilever portion. So now we have C equal to LF minus D upon 2. So 2.8 minus 0.5 upon 2, we will get it as 1.15 meters. Now already we know we have, that is the same on both sides. So we have this as 1.15 meter. Now you can see this. So from this we will find bending moment along YY direction. Because when I have this UDL along the length, This will gives me bending moment along y direction. So we have this as 500 into 1.15. We have this will be 1.15, because after multiplying it by width, we will get UDL along the length. And now along the length we have gives bending moment in y direction. And we will get this value 330.63 kilonewton meter. And now we have to multiply intensity along width, I have mentioned. So we have to multiply it by 2.8, gives us value along the width of the footing. Now I will not go in detail again. We have saved. Now as UDL, we have along this, and therefore we will get bending moment along XX. And then we have bending moment along XX, 356.06 kilonewton meter. And from YY and XX, we have M max, and that becomes 356.06 kilonewton meter. Now, knowing this value, we are in position to find depth from bending moment, for which we have to always design, that is balance section. So RU max, we have 0.36 FCK KU max, 1 minus 0.42 KU max. Substitute values, we will get it as 2.76 Newton per mm square. Now I will not go in detail with this. So now you can see this. Now we have to always provide offset that is beyond face of the column, and that is for form work purpose. And therefore we will get that is BXX. So this we have that is 500 column, and then we have this as 50 on this side 50. So BXX we will get it as 600 millimeters. So knowing this, knowing value of bending moment, we are going to get value of D, that is equal to 463.69 millimeter, which is depth of footing. That is effective depth of footing. So now we will provide cover and gives us overall depth. Now, in this case, actually, if you will go with this depth, then you are not going to check, you are not going to satisfy check that is one-way shear and two-way shear. So it is always preferable to increase this depth to overall by adding it 130 millimeters to 250 millimeter. This is again, sorry, 150. This is again a thumb rule, not given in any book. But if we will go through the book, they are suddenly increase it, and this straight portion is generally provided. This is of 150 millimeter. And generally this value, we have to increase from 130 to 150, round up it. So if we will go 130, then we will have this as 593, and 150, that is on higher side. So we can go overall depth as 600 millimeter. After this adding, you consider that depth as overall depth. Now anyone can go 625, 575, but if check is not satisfied, then you have to revise the depth. So now knowing this depth, dx, we have 600 minus 6540. So dx we have bar along x, and we have till center of this. So this is center, we have 60 millimeter. So this bar diameter we are going to generally consider 10 millimeter in this case. So we have this will be till center. And dy, that is in other direction, we have bars in other direction, will be in this fashion. So actually this is also considered 10 millimeter. So 10 millimeter, 5 millimeter center of this, and 5 millimeter center of this. And so total 10. So till this we have 70. And therefore in y direction we have 70, and in x direction 60. Half diameter of bars in x direction and half diameter of bars in y direction. Assuming diameter of bar 10, already I mentioned it. Now reinforcement, we have to find ASTX. So while finding along x direction, we have this depth as 540, and width we have that is 400 millimeter. because width of column is 300 plus 50 plus 50, and we will get it as 400 millimeters, because that we have seen we are in this fashion and x-axis we have in this way. So this will be my width, that is 400 millimeter. 300 plus 50 50, we have that as offset. So we have x-axis along this, means if I will draw this diagram actually, then we have 50 mm offset on both sides. So we have in this fashion, and then we have bending moment over here, and then we have this value b 400 into 540. This is dxx, and this I can say bxx, and from this we will get astx, and that is 2134.25 millimeter, diameter 10 millimeter. So 10 meter diameter, find area of one bar and divide it by 2134.25. So now we will go to the next along y direction. So we have this value. If I will go for 6 mm, 28 for 8 mm, we have this area that is 6416, so it goes to 50. And if we will go for 10, then we have 5 by 4 into 10 square, and then it comes 78. So you can have 2134.25 upon 78. So I will just calculate 2134.25 divided by 78. So we will have this as 27.36. So this comes 27.36. So we have provided 28. Then along y direction, now your b becomes d plus 50 plus 50. So this I will say byy, and this 500 plus 50 plus 50. And this is dy. And from this we will get this value of ASTY 2168, and we have same bars, that is 28, both along both direction we have same diameter. Now go to check depth for two-way shear. So two-way shear we have always at dy by 2 from face of the column. Dy we have effective depth along y direction from face of column. Now you can see this, we have this will be column and dy by 2. So we have dy by 2 on both sides. So this will be my critical section. So this is a red dotted line, you can see we have critical section. And if we will go to the dimensions, so you can see we have this as b plus dy. Effective depth y by 2 on this side, and also we have on this side. So it becomes total dy. So it total b plus dy. So b plus dy, and that is 0.83, and d plus dy 1.03. So this is our critical section. So perimeter of critical section, so we have 2 into 1.03. So we have calculated perimeter of this rectangular section, and we will get it as 3720 millimeters. Area 1.03 into 0.83 comes 854,900 millimeters square. Then we can have this, you can see this elevation of this, you can see, or front elevation I can say better. So we have this will be, if I will write it, so we have dx 60, then till center of this we have dy. So you can see this dx is shown till center of horizontal bars, and these dotted bars we have along y direction, and we have shown dy. Now we are interested to find depth of footing, and that is at critical section, means at this section. And now we have to find it where we have this section, so we have to find this value. Now you can see we have this value, that is equal to 0.215. Now you can see we have this value, if we will see, we have total this value, that is equal to dy by 2. Dy we have 530. So we will get this value by 2. So it comes 265. Now we have 50 millimeter, that is offset. So if I will subtract 50 millimeters, then I will get this value beyond offset as 0.215 meter. Now this is 0.45 because we have taken 0.15, and overall depth, if you will see, so we have 600 meter. So it becomes 0.45 meter. So 0.45 plus 0.15, it becomes 0.6 meter, that is 600 millimeter. Now we have to use similar triangles, and by similar triangle, we are in position to calculate this value that is shown by y, and subtracting y from 0.45, I will get and add this value, that is still this. How much value we have this? So we have 70, and then subtracting 150 minus 70, because we have effective depth, effective cover is 70 millimeter. So 150 minus 70, so we have 80 millimeter. Once I got value of y, then I will subtract y from 0.45 and add 80 millimeter in this, then I will get value of DC. And that is calculated over here. You can see I have calculated value of y. Knowing value of y, I will get DC, that is dy minus y. So now that also we can go directly. Dy we have till this. If I will subtract y from this, then you will get this value. Or another, I already mentioned this. We have 0.45. Then we can have, from this, we have to subtract y. So 450 I can say, minus y we have, that is minus y we can have 87.9, and then we have to add 80, and likewise we will get in this fashion, because we know 0.45 plus 80, again 530, which they have considered directly over here. And then resisting area at critical section. Now we know perimeter we have calculated, depth we got from here. So multiplication of this perimeter in last step, if we will see, we have this perimeter value. We have calculated over here, perimeter 3720, underline we have made over here. And depth we have calculated just now. And knowing this, we are in position to calculate resisting area. Now knowing resisting area, we can find shear strength, for which we require permissible shear stress, given clause number 36.6.3.1 in IS code, where we have Ks tau c. Now you know this, I will not go in detail, and from this I will get value of tau c. This is for limit state, we have 0.25, and for working we have 0.16. And knowing this, we can calculate tau uc Ks1, because we have that value greater than 1 d upon bs. So now shear strength, from this we will get 1841.97, and we have shear area at critical section. So now we have calculated actual bearing pressure, which is 192, and area at critical section also we have calculated, that is 0.8459. So 2.86 minus 2.6, we will get 1237. Now try to understand how we have calculated this. We have, this will be area of footing, that is overall. So we have this as 2.6, we have this 2.8, and then we have inner area. We have this inner area, that is 1.3 and 0.83. So just go there and see it. And then this area we have calculated, because this is also known as punching shear. Punching shear means this will give us punch and it will go down, that is below. Punch means that portion only go below, and therefore it is known as punching shear, and therefore this will be shear force. So this area we have considered. So critical, I will just go over there. So we have critical area. So I can just go beyond. Is it correct? 1.03 and 0.83. So 1.03. So this is not 1.3, 1.03 and 0.83. So that area we have subtracted. This dotted line area we have subtracted, because it will go down and remaining portion will develop shear force. And this is greater than actually strength of this, and therefore it's okay. Now we will go for check depth for one-way shear, which will be at dy from face of the column. Now video will be larger time, but do not have any option for this. Now it is always at dy from face of the column. And now you can see this will be my critical section. Now 0.3 plus 2 into 0.3. In last, that is for two-way shear, we have 0.3 plus dy. Now here we have 0.3 plus 2 dy, and this will be 1.36 and 1.56. So this will be our critical section. Now, if I will subtract this 1.56 from this 2.8 and divide it by 2, then I will get this value, that is 0.62. Now this you can calculate, 2.8 minus 1.56 and divided by 2 will be 0.62. And then now I made it at hatch, that I will tell you afterwards. Now here we have to find, actually this will be my resisting area. So this I am interested to find out this trapezoidal, and then I have to take this as total. That is effective depth we have to consider over there also. So we have to find this area, multiply this area by again permissible stress, and then we have to check that for the force, shear force, which will be developed by this hatched portion. So now we will go with again this same way. Now at dy we have to find this depth, and in the same fashion we are going to calculate it. Now by 0.48. Now again in the same way we have till this 0.53, then we have 0.05 will be offset, so 0.53 minus 0.05 gives us 0.48. So we have y upon 0.48 and 0.45 upon 1.1. Now 1.1 also you can calculate, total 2.8, then we have 0.5 and 0.5 and this 0.05, so 0.6. So 2.8 minus 0.6 divided by 2. And this comes 2.2 by 2, that is 1.1 meter. So now in the same way we have calculated value of DC, and now we have calculated this area. Now I already mentioned we have to consider till center of this, that is still effective portion, and this depth already I told you 150 minus 70, it becomes 80 millimeter, 0.08 meter. And now this area are calculated for trapezoid and this rectangle. Now you can see this area at critical section, 0.08 into 2.8, because this is, we have rectangle. This portion we have rectangle, and this portion we have trapezoidal. And for trapezoidal, 1/2 summation of parallel sides into depth. So likewise, we have this area at critical section. And now shear force at critical section, I already mentioned. So shear force at critical section, this hatched portion. So that I already mentioned. So we have this as 2.6 meter, and then this is 0.62. So what we are going to consider, this portion will go below, and due to this shear force, which will be in hatching portion. And we have this 310 kilonewton, and now we have to see this strength. So we have first find this nominal stress, 0.4. This is developed due to shear. And our tau C, that is tau UC, we should have greater than this. Now we know percentage of steel is 0.38 because we have provided 78.5, and that is 25 bars. And then we will have this as tau UC greater than 0.42. Actually, we have provided 28 bars. So just see, there may be a little change in calculation, but 0.38 and this value little bit we can have, that is on higher side, maybe 0.3 or 0.4, but is greater than 0.4 Newton per mm square. So this is okay. Means our check, that is satisfied. So if we will take it as 28, then again you are on safer side actually. And then this will be last check, that is bearing pressure, clause number 34.4 in IS 456. So PU, that is column load upon area of column 9.33, and then A1 is BF into LF. Already we have calculated. You can see this, you can read this. So we have to consider it as lower base of largest frustum and all this. So do not go in this one. Just you should know. Therefore, I have mentioned over here. So you will get it as B plus 4df and D plus 4df. This is B and D. These are column dimension, and this is depth of footing. And from this you will get value of A1. Then you have A1 is minimum of 2. So it will be 7.28. Then A2, B into D, that is area of column. And from this you have to see this value. If greater than 2, then we have to take 2. In maximum 99.99% problems, this value is 2 only. Then we have permissible bearing pressure, that is 0.45 FCK root A1 by A2 is 2, and this is 18 Newton. This is permissible bearing pressure, 18. And actually we have calculated, you can see this is 9.33. And this will be greater than, so this also satisfied. Now development length, you know, I will not go and again explain this. We have that formula, length, development length available. We have 1/2 BF minus B, that is beyond face of the column. We are actually mentioning because we are talking about the cantilever portion only. So available is 1090 and required is 470.12. So we need not require to go more again in this. So this is all about your footing problem. Now we will stop here. Thank you.